Okay, so question 21 starts by asking us about this isotope and asks us just to figure out what particles it's made up out of. So we look up silicon on your periodic table and you find that it says something like that. So that's the atomic number, which remember is the number of protons. So we can straight away write down that it has 14 protons. That number is the mass number, which is protons plus neutrons. So if we take protons away from the total, which leaves us with 16, that's the number of neutrons. And the electrons, well, it's an atom, and if it's an atom, the protons and electrons have to have the same numbers, so that the charges will balance out. And so it has 14 electrons as well, and that's that one. Then we're asked to calculate the relative atomic mass of silicon in the sample from these data here. So remember, relative atomic mass is just a weighted mean, which means what you do is for each of these isotopes you calculate the mass number times the amount there is. So we'll have 28 times 92.23 lots of that, plus 29 times 4.68 lots of that, plus 30 times 3.09 lots of that, and you divide by the total of the amounts, and since the amounts are percentages, obviously they just add up to 100, and if you compute that, it comes on your calculator to 28.1086. But you have to read the questions very carefully all the way through and check always what level of rounding does it want, and in this case it says 2 decimal places, which means you're going to cut it off there. But remember that you've got to think about, does it round down or up? And in this case, because that number 8 is bigger than 5, it rounds up, so it's 28.11 to 2 decimal places. Part B, we're focusing on this molecule, which is phosgene, and it asks for a dot and cross diagram. So you just put carbon in the middle, and then oxygen and the 2 chlorines, following the structure it's given us. And remember that, I mean, there are lots of ways you can do this, but what I would do is start with oxygen, and remember that oxygen will basically always end up with 8 in its outer shell, unless it's some strange unstable structure. But in a neutral, stable molecule, oxygen is always going to end up with 8 in its outer shell, and the way it's going to do that usually is by forming a double bond if it's only bonded to one thing. So because it's got 6 electrons of its own, and it can bring in 2 more by forming a double bond here. So that's a good place to start and say, right, okay, that's all 6 of the oxygen's electrons accounted for, 2 lone pairs and a double bond. Chlorine is in group 7, so it only needs 1 to complete 8 in its outer shell, so we would expect it normally to form a single bond. So let's see if that works. If we just put a single bond there and there, that leaves each chlorine with 3 lone pairs, which need to be shown like that. And then we just need to check that that's okay for the carbon. But it's fine, because we've used 4 electrons that the carbon had. It's brought in 4 more, so it's taken it up to 8. So that's correct for that one. Okay, then it wants to know what shape that molecule will be. So remember, what we do is we look at the middle atom and we ask how many double bonds, how many single bonds, how many lone pairs does it have. So in this case, we can see that the carbon has 1 double bond. It has 2 other bonded pairs. And it doesn't have any lone pairs, but it's worth writing that down just to make sure that you've thought about lone pairs, because obviously they do affect the shape when they're there. So that's what the carbon has. And the important thing that you must state in your answer is that these repel each other. So that needs to be written down, that these are repelling each other. Oops. So when you just have 3 things repelling each other like that, the shape you get is trigonal planar. So try and get that word right. It's not triangular, it's not triagonal or anything like that. So just in case they're being picky about the word, it's trigonal planar is the word for that one. last little bit of that, silicon, carbon, oxygen, chlorine are called p-block elements because their highest energy electrons are in a p subshell. So just be slightly careful with the wording here. You can probably get away with saying outer electrons, but it's better to say highest energy electrons, and in a p subshell or in a p orbital, but not in a p shell. Remember, you've got to get the right word. Subshell or orbital would do for that one. Okay, that's question 21. Okay, so question 22. In terms of the number of electrons transferred, explain whether magnesium is being oxidized or reduced. You've got to make sure you answer the question there, because it says you've got to talk about the number of electrons transferred to or from the magnesium. So you've got to think about what's going on in this compound, and obviously you know magnesium's a metal, so when it reacts it forms positive ions. So what you've got there is 3 lots of Mg2+, as well as 2 lots of PO4 3-. So the point is that magnesium's gone from atoms to 2+ ions. So the point is that each magnesium atom loses 2 electrons. And if you lose electrons, remember the old mnemonic oil rig, oxidation is loss, reduction is gain. So if it's lost 2 electrons, it's been oxidized, is the answer. But to get that mark, you had to say that it loses 2 electrons, because it says in the question in terms of the number of electrons transferred. So if you just say it's lost electrons, that's not enough. You've got to read these questions really very carefully. So then we come to this calculation, and it wants to know the mass of magnesium that we need to react with the phosphoric acid. So the information we have got is that we've got 50.0 cm cubed of 1.24 moles per dm cubed of phosphoric acid. So the starting point, as always in any calculation, is we've got to get moles, and the recipe for that is moles as concentration times volume in dm cubed. So we put the numbers in. Concentration is 1.24, volume is 50 cm cubed, so that's 50 over 1,000 in dm cubed, and that comes to 0.0620 moles of H3PO4. And then you think, right, but we're being asked how much magnesium. So then you've got to go to the equation, because the moles are not the same. You can see that it takes 3 moles of magnesium to react with just 2 moles of H3PO4. In other words, however many moles of H3PO4 you've got, it will be more moles of magnesium by a factor of 3 over 2. So that's what we do next, is get that the moles of magnesium is 3 over 2 times the moles of H3PO4. So it's just 3 over 2 times that number, which is 0.0930 moles. Then we've got to turn that into a mass. So we just get mass is moles times AR, which is 0.0930 times 24.3, which is the atomic mass of magnesium, and that comes to 2.2599. And as always, you look to see about rounding. Does it ask for a specific level of rounding? And it does. It asks for it to 3 significant figures. So 1, 2, 3 means it's cut off there, and clearly that's going to round up to 2.26 grams to 3 significant figures. Okay, and that's that bit. Right, so this is the reaction, and the important thing is that we've got to get a sample of solid magnesium phosphate at the end. Now if we were to add just enough phosphoric acid to react with all of the magnesium, we wouldn't just have this at the end. Of course, the hydrogen will escape, that's not a problem because it's a gas, but we would still have the water that this is dissolved in. And so you've got to separate it from that. That's the key thing. Okay, so the first thing you're going to have to do is to filter it. Okay, so you filter off the solid, and that will get rid of the water. But it's still not pure because it's still going to be wet. And if there was, for example, any excess phosphoric acid, if you added slightly too much, it'll still be contaminated with that as well. So the next thing is that you wash it. That means that you just run some cold water through it to wash away any phosphoric acid that's still there, and then you dry it in an oven or just by leaving it out in the air. So to get the full marks for that, you need filtration, then washing it with cold water. Don't just say wash it, you've got to say with what. But we know it's insoluble in water, so wash it in water, and then dry it in an oven, and that would complete the method. Okay, so then it wants a reaction of some magnesium compound with phosphoric acid, which can produce magnesium phosphate. So this is really just testing your acids plus bases stuff. So you could choose the oxide, or the hydroxide, or the carbonate, really. Any of those would be fine. But it's got to be one of those bases that reacts with an acid. And so if we choose magnesium oxide, for example, we would have magnesium oxide plus H3PO4 goes to magnesium phosphate, which is that. And acid plus oxide goes to salt plus water, so water's your other product. And that obviously needs a little bit of balancing. 3 magnesiums there, so that needs to be a 3. 2 phosphates there, so that needs to be a 2. And you can see that that gives you 3 waters, because you've got 6 hydrogens and 3 oxygens. So you get that as your other product. It doesn't ask for state symbols. Always check whether it asks for state symbols, but it doesn't in that case, so that's fine. You don't need to add them in. Okay, so now we've got this reaction of H3PO3 decomposing to make phosphine, and it's asking us, give the amount of H3PO3 to calculate the volume of phosphine. So the starting point is, again, to look at the equation and to realise that for every 4 moles of H3PO3, you only get 1 mole of phosphine. Okay, so the moles of phosphine is not that, it's a quarter of that. Okay, so that's your first step, is to get that the moles of PH3 is a quarter of the moles of H3PO3, and a quarter of that number is 8.00 times 10 to the minus 3 moles of PH3. Okay, so that's the first step. Then we've got to use the ideal gas equation, because it gives us a specified temperature and pressure. We can't just use the approximate 24 method. Apart from anything else, it's not room temperature. So we've got to use the ideal gas equation, which is this. And the first job is to rearrange it to figure out what the volume is. So we've got to move the pressure over to the other side. Remember, things slide diagonally from one side to the other. So if it's on the top line on the left, it will move to the bottom line on the right. So you get V is equal to nRT over P. Write that expression down before you put any numbers in. It's an absolute golden rule in all these chemistry problems. Rearrange the expression algebraically, then put the numbers in, because it's almost impossible for people to figure out what you're doing if you just do it with the numbers. So rearrange the expression first, and then we can put the numbers in. So N is the number of moles, which we've just got, 8.00 times 10 to the minus 3. R is the gas constant, that comes from your data sheet, 8.314. And T is the absolute temperature in Kelvin. So it tells us 200 degrees C, but you've got to remember to convert that to Kelvin by adding 273. Nobody tells you how to do that in the exam. You have to memorize that Kelvin is degrees C plus 273. So that will be 473 degrees C. And P is the pressure in pascals. So it tells us that it's 100 kilopascals. But remember, a kilopascal is 1,000 pascals. So if 100 kilopascals is 100,000 pascals. So it's 100,000 on the bottom. And if you crunch all those numbers together, you get 3.146 times 10 10 to the minus 4. And that will be in cubic meters. Okay, so this is the one chemistry calculation where the volume isn't in dm cubed, it's actually in cubic meters. And you have to remember that. So on the answer line, just to be helpful, they didn't ask for cubic meters, they asked for cubic centimeters. And you need to know the relationship. So there are 1,000 cubic centimeters in a dm cubed, and there are 1,000 dm cubed in a cubic meter. So therefore there are 1,000,000 cm cubed in a meter cubed. So we've got to multiply by 1,000,000, okay, which gives you 314.6 cm cubed. But again, you look to see, does it specify a level of rounding, and it doesn't in this case. So you could leave it at that, but really you don't know it that accurately, because these numbers, you know, like this one and this one, you only know to 3 significant figures. So you could round it to 3 and say 315 cm cubed. But in this case, it didn't matter if you didn't, that would have been the right answer. Okay, so the last little bit of this question is asking about phosphine burning in air. So we're going to assume that means that it's reacting with oxygen in the air and to form P4O10 and water. And it's relatively easy to balance because we're stuck with 4 phosphoruses in P4O10, so that's going to have to be 4. And that gives us 6 hydrogens. No, it doesn't. 4 3s are 12 hydrogens, so therefore 6 H2O on the right hand side, and that just leaves this number to work out. So we've got 10 oxygens there, plus 6 makes 16 altogether, which is 8 lots of 2. So that's your equation. That's it for question 22.